So we got a potato, right? We're boiling a potato, and we're taking it from a pot that's on the stove, and we're letting it cool in our kitchen. Very exciting. Okay? And they give us all this crap that like the internal temperature of the potato is 91 degrees, time t equals 0. That's going to be important. So we are going to give it an initial temperature. Okay? And we know that the temperature is greater than 27 degrees. Okay, that may or may not be important. It sort of is. It's not like going to make or break your ability to do the problem, but it's a good thing to know. And we know that it gives us this differential equation to model the internal temperature of the potato. Okay? And they're saying the internal temperature of the potato is H. Okay? Where the dH dt is equal to this thing, negative 1/4 of H minus 26. Okay? So if we wanted to find a function to represent the temperature of the potato, we have to integrate this, right? That's how a differential equation works. We integrate dH dt to get H. Everybody good with that? Okay. But that's not what it asks us to do. First thing it asks us to do is write an equation for the tangent line to H at t equals 0. That's something we did with the other differential equation FRQs also, right? That should be pretty straightforward, I hope, but we're going to work through it together just to make sure. So it says, write an equation for the tangent line at t equals 0. Yes? That means we need a point. We need the point when t is 0. What is the value of H when t is 0? 91. And that's the initial condition they gave us. That's important. We also need the slope when t equals 0. Okay? Well, the slope when t equals 0 comes from dH dt. At the point 0, 91. So we need to evaluate dH dt at 0, 91, just like we did with the other ones, right? This is the same, nothing really different here. Yeah? All right. So we do that, we plug in 91 into that because that's what H is. There's no t in there, so we don't have to worry about that. What's 91 minus 27? 64? Does that sound right? Yeah? Okay. So we have negative 1/4 of 64, which ought to be negative 16. So for part A, we're going to write the equation y minus 91 equals negative 16 times t minus 0. That equation is good enough. You could have written it as just negative 16t. You could have done y equals negative 16t plus 91 on the right-hand side. That'd be fine too. Any of those are fine. None of them is better than the other. None of them will get you more points or less points than the others. Personally, I just always write it in point slope form because we have a point and a slope. And then I find no reason to simplify it because it doesn't matter. And it just gives you a chance to make an arithmetic error. And one thing I've noticed about you guys is you're awfully good at making arithmetic errors. So just kidding. Okay. So don't do extra work that you don't have to do though, because solving that for y takes an extra 15 seconds to do it and write it out. It's a waste of 15 seconds. You don't need to do it. Okay. All right. So that's the first thing. Second thing is we want to use that equation to approximate the internal temperature of the potato at t equals 3, which means we need to plug in 3 for t. Easy enough. Right? So we'll say y of 3 is negative 16 times 3 plus 91. And what does that come out to be? I think that's 43. Negative 48 plus 91. Does that sound right? Somebody left. They had enough already. Does that sound right? 43 degrees? Yeah, I trust your arithmetic. Even though I just said you all make arithmetic errors. I still trust you. That's part A. Everybody good with part A? Okay. Now, part B is something that often happens in this type of differential equation. And you know, I say this type of differential equation. Well, the other ones, they didn't get, it wasn't like a quote unquote real world situation. Because how often do we really care about the internal temperature of our potato after 3 minutes? I mean, we just cut it open and they're like, it's too hot to eat still. I'll let it sit there and cool on. Right. So like this is a real world situation differential equation. Whereas the other ones, like it was just dy dx equals xy squared or something, right? And you do a slope field and all that stuff. Right? Occasionally in those, they'll ask for a second derivative. And these ones, they will almost always ask for a second derivative. Okay? And so we need to remember that when we take the second derivative of this, we're taking the derivative with respect to what variable? No. With respect to t, the thing in the denominator. We're taking the derivative of dh dt with respect to t. So we have dh dt was equal to, oh no, I forgot what was it equal to? Negative 1/16 times h minus 27, negative 1/4 times h minus 27. Yeah. So if we're going to take the derivative of this with respect to t, I'm going to write this out. Second derivative of h with respect to t is the derivative with respect to t of negative 1/4 of h minus 27. People at home, are you good with that?
Yeah.
People here, you good with that? Okay. The negative 1/4 is just a constant, right? Y'all agree that's just a constant? So that can just stay there. So we're still going to have negative 1/4. And then we're going to have the derivative of h minus 27 with respect to t. So what's the derivative of h with respect to t?
dh dt or ddt?
Yeah, dh dt. Exactly. dh dt. And what's the derivative of minus 27 with respect to any variable? 0. Right? So I end up with negative 1/4 dh dt. This is not the answer they want. They want negative 1/4 times dh dt. They want you to rewrite this negative 1/4 times h minus 27 down. So they want you to get 1/16 of h minus 27 as your second derivative. Everybody good with that? Any issues there? At home, are you good with that?
Yeah.
Wonderful. Okay. That was not all it asked, though. It had a second part to part B. It said, is your answer from part A an underestimate or an overestimate of the internal temperature? And this is something that they love to ask in these real world differential equation FRQs. Okay? Is there approximation from the tangent line an underestimate or an overestimate? So we have to think about this. Our function had a second derivative of 1/16 times h minus 27. And the problem originally said that the temperature, H, was always greater than 27. If H is always greater than 27, what can you tell me about the second derivative? It will be, what sign will it have? If H is greater than 27, it will be positive. If H is greater than 27, the second derivative is positive. Everybody agree with that? If the second derivative is positive, what does that tell you about the function itself? That it's concave up. Exactly. Everybody at home okay with that? Understanding why the second derivative is positive and that makes it concave up?
Yeah.
Everybody, not just Nick?
But what if it's smaller than 27?
Oh, wrong page. It's not. Because it says that it is greater than 27 for all times t greater than 0 initially in the problem. So we don't have to worry about it being less than 27. Good?
Yes.
Wonderful. All right. So everyone agrees that this function is concave up for all t values that we are concerned with. Okay. Great. Why do we care? Well, we care because that's what tells us if this thing is an under or an overestimate from our tangent line. Here's a function that's concave up, like our function is. True? Let me draw the tangent line at a point. Any point, doesn't matter. Here's my tangent line. Now that's my tangent line at 0. Let's say it doesn't really matter because that's what the problem said was 0. We're approximating at 3. There's 3. Yeah. tangent line gave me this value. The true value is up here. So is our approximation an underestimate or is it an overestimate? It's an underestimate because this value, this y value, is lower than this y value. Draw the function concave up however you feel like. If you draw it concave up, the tangent line will always be an underestimate, 100% of the time. You will find this written in that document that I have put in Google Classroom for you with all of the millions of important things that you need to know. Okay? But this is important. If a function is concave up on an interval and you approximate a value on that interval using a tangent line, that approximation will always be an underestimate. Everybody good there? Now, what if, this is not the case, but what if our function had been concave down? Well, here's our tangent line now. Oh, that's not what I meant to do. Let's try that again. There's our tangent line now. And if I were to approximate the value using the tangent line on an interval where my function is concave down, then that approximation should be an overestimate. Okay, easy enough. I mean, visually, I think that's pretty easy to see, right? Yeah. Okay. Very important. Okay. Now, you will also find in a similar place in that packet a thing about secant line. You remember what a secant line is? What's a secant line? Okay, a secant line, yeah, is a line that goes through more than one point of your function, right? So here's my secant line for a concave up function. Sometimes they will ask about a secant line. If they do, the secant line on an interval where your function is concave up, the secant line is an over approximation. Everybody good with that? If the function is concave down, your secant line will underestimate it. You all see that? This is less common, but it does show up occasionally on the exam. Everybody at home okay with that?
Yeah.
You're okay with that? Any questions, anybody? Yeah. So our question asked that we came up with concave up, and then we said it must be an underestimate, right? That's what we said first. Somewhere right out there. Good or no? Yeah? Good? Yeah. All right. So that's all of part B. Part C then says for t less than 10, they give a different model for the temperature of the potato that only works for 0 to 10, as dg dt equals negative blah, 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 blah. And they want us to find g of t. So this is the part where they're asking us to actually solve the differential equation itself. Okay? So we're going to use dg dt equals negative g minus 27 to the 2/3. Here we have dg dt equals negative g. That's a 6. That's not a g. G minus 27 to the positive 2/3 or the negative 2/3? Positive 2/3? The 2/3. Okay. All right, everybody good there? Now, if you have not looked at one of these in a while, or have never seen one, this can be a little bit confusing about how to solve this differential equation, because we can't just, and we only have one variable, right? And normally when we just have the one variable, we just integrate and we're like, all right, cool, we're good, right? But that's not the case here, because the single variable that we have is not t. If we just have t over here and some constants and some function stuff with t, then we can just integrate and that's fine. But we don't, we have g over here. And if the variable on the right-hand side is the variable in the numerator of your differential piece, then you have to separate the variables. So if g appears over here anywhere, which it does, we have to separate the variables. Just like if we had dy dx equals blah, 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 x, y to the 7, because y appears over here, we have to separate the variables. So same here. G appears over there, we have to separate the variables. Everybody at home good with that?
Yeah.
Yeah. People here good with that? Yeah. Yeah. So we separate the variables by saying dg over g minus 27 to the 2/3 equals negative, we can say -1 if we want dt. Might as well put the -1 there. I will always personally leave any constants on the right-hand side unless I see a specific reason to bring them to the left. If there's a specific reason, like you're going to have to do a u substitution over here or something, and bringing a 2 over here makes it so that you can immediately eliminate that 2 because it's part of the du or something, cool, bring it over. That doesn't happen very often. I will almost always leave that constant on the right hand side. That's how they do their scoring guidelines. That's how I was taught to do it. That's how you should do it. Okay? Good? Wonderful. Okay, now we integrate. I integrate both sides. This side is easy. This side just becomes negative. Negative. If I integrate -1 dt, I should get negative t plus a constant. Okay. On this side, I got to deal with this a little bit more, right? This is actually a u substitution because this is a function being raised to the 2/3 power. The 2/3 power, not a problem, right? In fact, it's really, we're going to write this off the side to do all the work. Really, we would probably want to write this as g minus 27 to the -2/3, like this, right? Because then that's just the power rule once we get rid of the g minus 27. Right, the g minus 27 makes us do a u sub. So we're going to let u equal g minus 27. And then we'll note that du is just dg. So we really end up with the integral of u to the -2/3 du. Everybody's good with that? I hope. At home, are you good with that?
Yep.
Anybody have any questions on that at home? All right. So we integrate u to the -2/3. That goes up to u to the positive 1/3. We divide by 1/3. Okay. So that should become, if we divide by 1/3, that should be 3u to the 1/3, or 3 g minus 27 to the 1/3. And we don't need to put a constant on the left-hand side, right? Because constant on the left and a constant on the right is just constant on one side or the other. Now what do we have to do? This is the part sometimes people forget about. We need to solve for our
Constant.
We need to solve for our constant. So the initial condition we were given was that when t equals 0, the temperature was 91, right? So we've got 3 times 91 minus 27. So the 1/3 equals 0 plus our constant. And our constant then should be, let's see, this is 91 minus 27, it's still 64. I hope. The cube root of 64 is 4, like it's always been, and 4 times 3 is 12. Everybody good there? So we got a constant of 12. So plug that in. Okay, so we've got 3 times g minus 27 to the 1/3 equals negative t. Right? Negative t. What did we say the constant was? 12. And then we solve for g. Divide by 3. I'm going to write this as 12 minus t just for fun. I don't know. Seems like then I have to write less things. And then we're going to cube everything. And then we're going to add 27. And there is our temperature. Good? Any issues there? All right. Everybody at home good with that?
Yeah.
Wonderful. Did it ask us to approximate? Yeah, what is the temperature at T equals 3, it says. So at T equals 3, 12 minus 3 is 9. 9 over 3 is 3. We have 3 cubed, so 27 plus 27. 4 degrees. Don't get all excited when you finish solving the differential equation. Go, oh boy, I'm done solving the differential equation. I'm done. Because you just lost the point by not plugging in 3, which frankly is probably the easiest part of the entire problem. Right? Any questions on that? We all feel okay about the potato? If you sat down at the AP test and they said that you were boiling, they won't boil potatoes. If you were boiling beets and they gave you, beets are delicious. They gave you some differential equation to boil beets, you could do that now. Yes? Riley, you sure? Okay. Just need practice. Okay. All right, good. That's what we're going to do. So, anybody at home have any questions on that? Or anybody here? People at home, you're good? You all there?
Yes.
Okay. You speak for everyone. Perfect. All right. So the next one that we're going to do, we're going to do the baby bird problem. Now I'm going to give you guys a few minutes to work on it on your own. There it is. There's the baby bird. Everybody see the baby bird problem at home? Okay. So I'm going to give you guys 15 minutes here to work through this. 15 minutes. You'll note that it is very similar. Not exactly the same, but fairly similar. All right. 15 minutes. Ready, go. We got a baby bird who's gaining weight. That's good, right? That's what it's supposed to do. And we have an initial condition that at T equals 0 weighed 20 grams. And we are given a differential equation dB dt that tells us how much it weighs after any certain number of days. I think days. Okay. We'll note that this is similar to the last one in the fact that the differential equation only includes one of the two variables. It includes the one that's in the top part of our differential piece. It includes just a b. And part A is a little different though. It says, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? This is, if they don't ask about a tangent line, they will probably ask about the rate of change at 2 different times. So that's what it's asking. Is it gaining weight faster when it weighs 40 or when it weighs 70? Well, we are given a differential equation dB dt, which tells us the rate of change of the bird's weight. So all we have to do is plug each of those in to dB dt and evaluate. See which one's bigger. The bigger one will be increasing more quickly. So dB dt at b equals 40 is what? 60 divided by 5, right? 12. And dB dt at b equals 70 is what? 6. So it must be gaining weight more quickly when it weighs 40 grams.
Mr. Bachelor?
Yeah.
Couldn't you also say that because 40 is farther away from the adult weight?
Say that again. The computer just made some weird sound.
Couldn't you say that since 40 grams is farther away from the adult weight than 70 is, that it's gaining weight faster because of the first sentence in the problem? That is proportional to the difference.
It's proportional to its adult weight and its current weight. Yes, you could probably write out an explanation that would make sense. They would probably give you the points for that, but what they are looking for like a concrete numeric reason why.
Okay, got it.
Yeah, so you're right that that first sentence does indicate that. But the best, the easiest way to show it is just by doing those two arithmetic things, I think, rather than trying to write out an explanation. But you are correct.
Okay, thank you.
All right. Explain our reasoning. Okay, so we say 40 grams, and then you would have explained your reasoning however you felt like that made sense. We say 40 grams because dB/dt at 40 is greater than dB/dt at b equals 40 and d equals 70. Be good enough. Or the rate of change is 12 versus 6 or something like that. All right, so for the second part, find the second derivative, right? Part B says find the second derivative of b with respect to t. So we will do that. Same thing that we did last time, where we're going to take the derivative of that thing with respect to t, which means what? Should mean that the 1/5 is the constant out in front stays. And we take the derivative of 100 minus b. What's the derivative of 100 minus b with respect to t? The 100 part is 0. Negative dB dt, right? The negative b becomes negative dB dt. Everybody okay with that? And then we have to replace the dB dt with the original dB dt. So we end up with a negative 1/25 of 100 minus b. Everybody good with that? Because of the negative here. Because of the, when we take the derivative of negative b, we get negative dB dt. Everybody good there? Okay. All right, now, why can't this graph be the actual graph of b? Well, we're asked to find a second derivative, so that's going to tell us something about concavity, right? And what do we know about this bird? Well, it sure looks like, according to the graph, that its weight is never going to go above 100, right? That its adult weight is probably going to be 100 grams. So what does that tell you about the second derivative? For b less than 100, because that's all we're looking at in the graph. For b less than 100, this should be concave. What?
Down.
Down, right? Because if b is less than 100, 100 minus something less than 100 is positive. And we have a negative 1/25 of that positive, which makes it negative. So this should be concave down. Well, is that concave down? That part right there that I just circled is concave up. Right? This is concave up. So your explanation would say something to the effect of the second derivative indicates that on the entire time between b equals 20 and b equals 100, the graph should be concave down. Yet half of the graph is concave up, therefore this can't be the graph. So similar to what we did with the second part last time in dealing with the second derivative and the concavity, but not exactly the same, right? Everybody good with that? Yeah. All right, and then part C, separate the variables, find the particular solution. So this is the bigger point value piece. And what do we have? 1/5 of 100 minus b. Yeah. So we'll separate the variables. As I said before, I will leave the constant on the right-hand side, and I will just bring the 100 minus b to the left. And we will integrate both sides. The left is a little more complicated, so we'll do the right first, 1/5 t plus our constant. And then on the left-hand side, what do we have to do to integrate that? We'll have to use these, we'll let u equal 100 minus b, which tells us that du is negative dB. So in order to get that dB that we need, or sorry, that du that we need to put a negative sign in there, which means we need to put a negative sign outside. Okay? So really now what we're looking at is negative integral du over u. And what's the integral of du over u?
Natural log absolute value of u.
Natural log absolute value of u, and our u was 100 minus b. Next step is solve for c. Our initial condition was that when t is 0, this bird weighed 20 grams. Is that correct? 20 grams. We have negative natural log of 80 equals 0 plus c, or a constant is negative natural log of 80. Everybody okay with that? People at home okay with that?
Yeah.
Wonderful. Okay. So now we go back in and we solve, right? We have negative natural log absolute value 100 minus b equals 1/5 t minus the natural log of 80. First thing we'll need to do is divide by a -1 or multiply by a -1. So we'll end up with natural log absolute value of 100 minus b equals, and this will become positive natural log 80 minus 1/5 t. Then how do we clear out the natural log of that thing? We exponentiate, so that will become just absolute value of 100 minus b equals e to the ln 80 minus 1/5 t. Everybody good with that? We're going to do 2 steps in one here. We're going to clear off the absolute value. Now, when we clear off the absolute value, I want to think about this for just a second here. We need to get positive values, right, for b. Right, so am I going to ever have a negative number over there? I'm not going to have a negative weight, right? So when I clear out that absolute value, I'm just going to take the positive version of it. We can confirm that if we want by saying, well, if I plug in 20, this will become 80. So I need this thing over here to be positive, right? And clearly it's going to be positive if I leave it as positive and not put a negative sign in front. Right? So we're going to leave it as positive. How can I simplify e to the natural log 80 minus 1/5 t? Pull the 80 out. So this becomes 80 e to the negative 1/5 t. And now we just solve for b. We'll add b and then subtract the 80 e to the negative 1/5 t. So we'll get b equals 100 minus 80 e to the negative 1/5. And that's our answer. And I don't know, did it ask us to approximate the, or to find the value of the weight at any time or not? No. So then we're done. Good or no? Okay. People at home, good?
Yeah.
Great. Okay, so here's what you're going to do. We don't have time to go through a whole nother problem, I guess, hoping. So tonight, I want you to go down to this problem. I don't know what page it is now because I've added a bunch of extra pages in. But it's the problem about the trash. At the beginning of 2010, a landfill contained a bunch of solid waste, blah, 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 blah. You'll note that this is similar to what we just did, yes? So tonight, you will do this problem. The trash problem, yes? It's page 9. You will do page 9. Right? Page 9, the trash problem. Right? Then, in addition to that, I would like you to let's see here. Which one do I want you to do? I'd like you guys to make an attempt at the first 2 problems on the rate FRQs. So rate FRQs. Problems 1 and 2. Note that the first one is calculator, the second one, oh, is also calculator. Look at that. Isn't that lucky? 2 calculator rate problems. All right. Tomorrow we will go over all 3 of those problems for sure. And then we will do probably another area or volume problem that you guys, from those 6 that you guys were already supposed to do, review another one of those. And then we're going to move on to another type of FRQ, the graphing FRQ problems, which are a little bit tricky to get started on. So I want to work through one of those first with you. The rate ones, I think you'll be able to figure out. As you're working through the rate problems, remember that the integral of a rate function gives you the amount of something. So if I have a rate at which fish enter the lake or a rate at which fish leave the lake, right? The integral of the rate at which they leave the lake is how many fish leave the lake. The integral of the rate at which they enter the lake is the number of fish that enter the lake. So keep that in mind. The integral of rate is the amount of the thing. So three FRQs to do tonight. Trash, fish, escalator. Trash, fish, escalator. That should be easy to remember. Trash, fish, escalator. TFE. This, fun, exciting. Trash, fish, escalator. This, fun, exciting.